Welcome to the incremental training for multi-source CTS related updates in IC Compiler 2 from L2016-03 SP1 to M2016.12. Please review the information on this slide before we begin. Links to incremental updates for multi-source CTS full flow are made available on the next slide. The remaining training slides cover the following features: manual clustering using the split clock cells command, on by default global route based tap assignment, multi-voltage support for multi-source CTS flow, namely for the create clock drivers and synthesize multi-source global clock trees command. Sub-tree level balancing in structural multi-source CTS. Please refer to the above links for the L2016-03 multi-source full flow training. Let us first go over manual clustering using the split clock cells command. DRC-driven clock cell splitting was introduced in 2014.12 SP1 through the command split clock cells. In 2016-03 SP1, split clock cells has been enhanced to support splitting ICGs such that they drive a user-defined set of load clusters. This can be used for custom flows requiring manual ICG splitting based on user requirements. To facilitate this, the dash loads option has been added to the split clock cells command. Dash loads takes a list of pin or port collections and cannot be used with the existing dash cells option. Each collection defines the set of pins and ports that need to be driven by a dedicated cell. All the pins or ports specified with dash loads must have the same driver. The command will then create a clone of original driver for each collection specified with dash loads. In this example, the orange gate originally drives sync clusters C1 and C2 along with the other loads, that is, the MUX in this case. Here, the user requirement is to have ICG clones for clusters C1 and C2 and keep the rest of the loads with the original driver. To achieve this, we call split clock cells with dash loads for clusters C1 and C2 as shown. This results in the structure on the right meeting user expectations. There are some special cases where cells are not split. For example, they are not split if the cells in concern are power management cells such as isolation or level shifter cells, or if port punching is needed on a power domain boundary. Cells are also not split if they have net connections with frozen ports or don't touch attributes, or if the cells themselves have size only, fixed or lock settings that restrict cell movement. Cells inside block abstracts are not split. User attributes, settings, and STC and UPF constraints are automatically copied over to the newly created cells and nets. Running the split clock cells dash loads command does not cause clocks to be propagated or the global router to be invoked. Post-splitting, the physical status attribute of the cells is changed to application_fixed. The set placement status command can be used to change the physical status in case the cell needs to be moved during optimization. In 2016-03 SP1, global route-based tap assignment is on by default. Let us go over this feature now. Tap assignment considering global route-based distance estimation was a feature in version 2015-06 SP3. This feature enables accurate distance estimation resulting in sinks being assigned to the closest tap driver. Global route-based tap assignment is enabled by the CTS.multisource.tap synthesis route-based estimation and is on by default in 2016-03 SP1. With the feature, we use global route-based distance estimation when assigning sinks to tap drivers. This honors CTS constraints, routing blockages, and accurately estimates if a net can route over a macro or needs to detour around the macro. In the example, without global route estimation, the tool considers the macro as a blockage and assigns the sink to a faraway tap driver, which will increase insertion delay. With global route-based tap assignment, it sees that the net can route over the macro and assigns the sink to the closest tap driver. This slide lists the results of using this feature on some designs. You can see an improvement in repeater count and area post-CTS with global route-based tap assignment. The feature is mainly helpful for designs with macros separating tap driver and sinks. Let us now review multi-voltage support for multi-source clock tree synthesis. Starting with version 2016-03 SP5, the following multi-source clock tree synthesis commands are supported for multi-voltage designs: create clock drivers, remove clock drivers, synthesize multi-source global clock trees, remove multi-source global clock trees. Multi-voltage support for create clock drivers and synthesize multi-source global clock trees commands is enabled by setting the following app option to true: cts.multisource.enable full MV support. This app option is off by default. In cases where we need to insert cells on physical feed-through nets or nets crossing power domain boundaries when no port punching is allowed, enable the opt.common.allow physical feed-through application option. This will create cells as power domain on instance. Let us review the MV support for the create clock drivers command. The power domain for the clock drivers is defined by their preferred location. This location can be specified using the dash boxes and dash locations settings in the create clock drivers command. Following this, clock drivers are inserted while avoiding port punching on domain boundaries and ensuring electrical correctness. Both library and template cell-based instantiation of clock drivers is supported. In the library cell-based flow, all cells are instantiated by the tool to create clock drivers. In the template cell-based flow, the user can specify a pre-existing cell, that is, driver of the net, to be cloned for the purpose of instantiating drivers. A multi-voltage clean input will ensure a multi-voltage clean output. Any MV violated nets are skipped with error messages. Remove clock drivers removes cells inserted with create clock drivers and restores the original clock structure without multi-voltage violations. Hierarchy selection in the library cell-based flow is done as follows. For a power domain with a single entry point, the power domain hierarchy is selected for repeater insertion. For power domains with either multiple entry points or multiple root hierarchies, the lowest common hierarchy of the loads or the hierarchy of the driver is selected for repeater insertion. The approach in case of multiple entry port or multiple root hierarchy power domains is also followed for power domains with no entry ports, such as when a physical feed-through net is present. We also need to make sure that the opt.common.allow physical feed-through application option is set to true. The repeaters are marked as power domain on instance. In all situations, loads within a power domain are connected to one of the drivers in the same power domain. Library cell selection is performed as follows. Single and dual rail cells can be specified with the -lib cells option. The first single dual rail pair in the list is selected by the tool. This pair must have similar delay characteristics for low skew, especially in case of H-tree drivers. The library cell is selected considering driver supply, supply of the loads in the given power domain, and available supplies in the power domain. In the template cell-based flow, the template cell hierarchy is retained for all of its clones. UPF constraints are copied to the newly created cells. In case a non-repeater template cell is specified, the library of that cell is used for cloning. The location of these clones is the voltage area and power domain of the template cell. In case of a repeater template cell, the -lib cells option can be specified with the -template option. This selects a dual rail or single rail cell similar to the library cell-based flow. The clones can be inserted in a voltage area different from the template cell depending on the preferred location. We need to ensure that the template cell is present in a voltage area that has at least one preferred location. In a case where the -short outputs option is specified, all cells with shorted outputs are inserted in the same hierarchy. Both single and dual rail cells must be specified using the -lib cells option if the drivers span across different voltage areas. Depending on the primary supply nets available, a mix of single and dual rail cells are inserted to ensure all loads are driven by the drivers. In case of multi-level clock driver insertion, cells drive loads at lower levels in symmetrical fashion without creating multi-voltage violations. Consider a simple example with 3 power domains and VAs. With the option -boxes 2x2, we divide the boundary or the core area in this case into 2 columns and 2 rows, resulting in a total of 4 boxes. The center of each box acts as the preferred location, which determines the power domain and the voltage area to be used. In this case, 2 preferred locations fall in the default VA colored in gray, and 1 each in VA1 colored in orange and VA2 colored in blue. Accordingly, 4 clock drivers are inserted. Loads in VA1 are assigned to one of the cells inserted in VA1, And similarly, loads in VA2 are assigned to one of the cells inserted in VA2. Rest of the loads will be connected to one of the drivers in default VA. The VA selected loads to be driven and driver supply determine the supply net and lib cell type required for a clock driver. Here, we use single rail cells as they meet the MV drivability requirement for each case. A few things to note are as follows. Power management cells, such as isolation cells or level shifter cells, cannot be cloned if being used as template cells. If the target power domain is a scoped power domain, cells cannot be created as power domain on instance. Let us now review MV support for the synthesize multi-source global clock trees command. The tool command determines repeater location to ensure a symmetric H tree meeting DRC constraints. The location of the repeater determines the power domain and voltage area the cell is inserted into. Similar to the create clock drivers command, hierarchy selection is based on power domain type and logical structure of the net being buffered. The cell type is selected, ensuring electrical correctness. Please set the opt.common.allow physical feed-through application option to true to ensure that cells are inserted as power domain on instance when required. The remove multi-source global clock trees command removes previously inserted H trees without creating multi-voltage violations. A few things to note are as follows. Single and dual rail library cell pairs with equivalent delay, capacitance, drive strength and other characteristics must be specified with the -lib cell option in order to ensure low skew. If multiple single and dual rail cells are specified, the tool pairs them based on list ordering. Cells without pairs are excluded and the pairing is solely order dependent. Specifying many library cell pairs can increase runtime. Hence, we can provide a single pair with identical delay characteristics. As always, an MV clean input provides an MV clean output. Consider a case with 3 power domains and voltage areas with tap drivers inserted as shown. Here, the H tree is built using both single rail and dual rail repeaters, ensuring MV correctness. Let us now review the subtree level balancing feature in structural multi-source CTS. Structural multi-source CTS preserves subtree levels during optimization by default. In 2016.12, it has been enhanced to balance subtree levels before synthesis. This ensures balanced subtrees as input for structural subtree synthesis, thereby improving QOR. The set multi-source clock subtree options command now has new options to support this feature. The -balance level option, when true, enables level balancing across the driver objects specified with the set multi-source clock subtree options command. The optional -target level option can be used only with the -balance levels true option to specify an integer number as a target number of levels. By default, the tool uses the maximum level out of pre-existing number of levels among driver objects as the target level. Different settings can be specified for each subtree set. The Remove Multi-Source Clock Subtree Options -target level command can be used to remove the previously specified settings. Report Multi-Source Clock Subtree Options command has been enhanced to report the specified settings. A new step called Pre-Process has been added to support an incremental flow if required. This is a step before merge. The -balance levels true option enables the synthesize multi-source clock subtrees command to balance subtrees such that each sink has the same number of levels. Buffers used for balancing are selected from the library cells specified for CTS. The driver object has a level count of 0. This count increments for each subsequent gate level up to and including the sink. If the target specified using the -target level option is more than the maximum pre-existing level, additional buffers are added close to driver object. If target specified is less than the maximum pre-existing level, balancing occurs only on subtrees with levels less than the target. The inserted buffers get a name with a prefix specified by the cts.common.userinstanceNamePrefix application option. Buffers driving ungated sinks get a default suffix of _UGS. That concludes the multi-source clock tree synthesis updates from L2016-03 SP1 to M2016.12. Thank you for listening.